Electromagnetic wave polarization. I've really been trying to make shorter videos, and I pared this down to what I think is a minimum set of information that just belongs together in the same video. And I want to start off by defining electromagnetic wave polarization, and I'll be referring to the IEEE definitions because this is a class in electrical engineering. From there, we'll take a deeper look and visualize. I think that's really important for polarization, but explain, visualize linear, circular, and elliptical polarizations. Then I want to take a look at combinations of linear and circular polarizations. For example, if you put two linear polarizations together in the right way, you get a circular. If you put two circular together in the right way, you get linear. Then we'll go on and we'll talk about the Poincare sphere, which is sort of a visual representation of all possible polarizations. We'll then get mathematical, and I will show you a polarization explicit form. It's a way to write an expression for a plane wave that makes determining its type of polarization very, very easy. And then last, a warning about conventions. Definition of electromagnetic wave polarization. Let me start with sort of a simplified, or the way I like to explain, what is polarization? Well, it's the property of an electromagnetic wave that's describing the time-varying direction and magnitude of the electric field. In other words, looking at a wave, what is the electric field doing? That's the polarization. So we can quickly, in frequency domain form, write an expression for a plane wave. And this vector out front is what is the polarization vector. And everything about the polarization of the wave can be lumped into that vector. Now let's take a look at the IEEE standard definitions of polarization. And this is of an electromagnetic wave. There are actually other ways polarization is used. For example, when a material becomes polarized and charges are displaced. So here we're talking about an electromagnetic wave. So IEEE defines it as the locus of the tip of the electric field vector observed over time at a fixed point in space in a plane orthogonal to the wave normal. Holy smokes. And so the visualizations we have coming after this, I think, will help. But that sentence is rather wordy for a very good reason, because we need to be really specific. And as you'll see, this is a little bit tricky. We'll see that there's kind of two types of polarization. There's linearly polarized waves and circularly polarized waves. Well, a linearly polarized wave, the definition, an electromagnetic wave for which the locus of the tip of the electric field vector is a straight line in a plane orthogonal to the wave normal. Again, a big sentence. Don't worry about not following all that. I have visualizations that are very consistent with this. Circularly polarized wave. An electromagnetic wave for which the locus of the tip of the instantaneous electric field vector is a circle in a plane orthogonal to the wave normal. This circle is traced at a rate equal to the angular frequency of the wave with a left-hand or right-hand sense of rotation. And that's where even more confusion will come into this, the difference between left and right hand. Before moving on, I want to talk about why polarization is even important. And the first two bullets really summarize everything here, but I have a few more that I'll add. But the big thing is the electromagnetic fields will behave differently around a device depending on its polarization. So just by illuminating the same device with a different polarization, we can get a different response out of that. The other thing is if we're trying to produce interference, so we have constructive, destructive interference, and there's a bunch of different ways we can utilize that to do filtering functions and other things. So if we're trying to utilize interference and we have orthogonal polarizations, that will not produce interference. So it is very important to understand the polarization so that we can get the properties that we want to out of our device. While all devices change their behavior based on polarization, I shouldn't say all, but almost all. This is particularly true when the size of the device approaches the wavelength. And if you were to stick me to put numbers to that, I might say anything that's 10 wavelengths and smaller, but it's not really a sharp cutoff. but certainly it's more important than a device that's incredibly large relative to the wavelength. As an example, lenses will focus different polarizations differently. So if you illuminate a lens with a linearly polarized wave, it will focus slightly differently along the two axes. If we're looking at reflection and transmission, for example, light bouncing from air off of water, the amount that reflects depends on polarization. And later on, when we study the Fresnel equations and scattering at an interface, we'll see how that works. If we have resonators, so we have a wave bouncing back and forth inside of something or circulating around something, well, the polarization can play an important role on that resonant frequency, and that's because fields pointing in different directions will interact with materials differently, they will travel at different speeds, and that can shift resonant frequency. So cutoff conditions for filters, waveguides, that kind of stuff all depends on polarization as well. And I'm probably not listing dozens of other things. Linear polarization. So a linearly polarized wave, and back to the IEEE definition, and I'll restate it and then show you in this visual here what's being said in words. So I'll repeat the definition. An electromagnetic wave for which the locus of the tip of the electric field vector is a straight line in a plane orthogonal to the wave normal. Well, okay, so the plane orthogonal to the wave normal is in the z direction. That's the direction the wave is traveling. So in a plane orthogonal, we're talking about the xy plane. And if we were to plot the locus of points, in other words, just record everywhere the electric field visits, it's along the x-axis in this case. And that would form a straight line. And I'm illustrating that with this plane that I've put here. But don't confuse the plane that I've put here with this plane orthogonal to the wave normal. In the definition, that plane is in the xy plane. I just like adding this sort of green transparent plane here because I think it illustrates the electric field is all falling on this straight line. So that's a linearly polarized wave. Now we can have a wave that's linearly polarized purely along x. That's what we saw on the previous slide, and that's what we see here. I also want to take one quick moment to mention when we draw waves, just using these arrows, it's easy for us to forget that this wave is really a volumetric thing and the field's very smooth and continuous. And I'm trying to show that with sort of these blue, fuzzy, cloudy regions here. And that really would be what the wave actually looks like, but it's hard to draw that with the polarization and everything. So we just draw the electric field along a single axis, even though it definitely exists off of that axis. So just keep that in mind. But really from this point forward, we'll just be showing those arrows off of the z-axis. So if it is linearly polarized in the x direction, then what I have in parentheses here is the polarization vector conveying the amplitude, and that's a complex number. So it can affect amplitude and phase, but it is in the x direction. We can very similarly have an electric field polarized in the y direction. Everything we said is still true. It's just that now the electric field is oscillating along the y-axis. So the polarization vector up here also has a complex amplitude, but it is in the y direction. To fully generalize this for a wave traveling in the positive z direction, we can have an infinite number of different types of linear polarization. And so we can explain that by giving it a tilt by this angle theta. So any electric field that's oscillating along a line, and it doesn't have to be along the x or y axis, anything oscillating along a line is considered a linear polarization. So what we're looking at here are all possibilities of linear polarizations, and we can call that theta the tilt angle. Later on, we could look at this immediately and know that's a linear polarization because we would look at the x and y components and see that they're in phase. That's just a foreshadowing of something that's coming later. Circular polarization. Let's start with the IEEE definitions of left-hand circularly polarized and right-hand circularly polarized. And I will tell you why I don't like these definitions. And when I visualize that, I'm going to visualize it and define it slightly differently that I think it's easier to remember. All right, so the IEEE definition, left-hand circularly polarized wave. A circularly or an elliptically polarized electromagnetic wave for which the electric field vector, when viewed from the wave approaching the observer, rotates clockwise in space. I'm not going to read the right-hand circularly polarized. It's the exact same definition, except it'll say rotating counterclockwise. The reason I don't like this is, and maybe this is just an American thing, but when we tighten a screw, we say that we're turning it to the right, going clockwise, or if we're turning it to the left, we're loosening it, we'll say that that is counterclockwise. Well, these definitions are the opposite of that. Left-hand circularly polarized is talking about a clockwise rotation, and then the right hand is talking about a counterclockwise rotation. I think that's very counterintuitive. And again, I don't know if this is an American thing. I'd love to hear from people in the comments if this is just an American thing, but I don't like thinking of it this way. Here's a visualization of how I like to define a left-hand circular polarization. And I like to think of this from the perspective of the source. So we are observing the wave in the same direction that it's propagating. We're looking down the positive z-axis, and the wave is traveling down the positive z-axis. From there, we pick a fixed point. So for convenience, let's pick this first point, and we observe the direction of the rotation. Now, to us looking almost down the negative z-axis, this looks like it's clockwise, but we have to remember, if we were this eyeball, looking down the positive z direction, this would look counterclockwise to us. So counterclockwise, left circular polarization. I think that's much more intuitive than the IEEE definition, where we would be observing it here down the negative z direction, and we would be looking at this rotating clockwise and saying, oh, that's left circular. I don't think it's intuitive to associate clockwise with left hand. I think most people associate clockwise with right hand. On to right-hand circular polarization. Everything is the same here, except notice the rotation here has reversed. And to the observer, this freaky looking eyeball, this is clockwise rotation. So clockwise would be right-hand circular polarization. Elliptical polarization. We've covered when the electric field traces essentially a line somewhere in the XY plane. We just talked about circular polarization. Well, the more general thing is ellipses. Suppose the electric field is still circulating, sort of like the circular polarization, but it's tracing out an ellipse. Well, this is called elliptical polarization. And that ellipse can be tilted at any angle. It could be fat. It could be skinny. That's all elliptical polarization. To make the point a little bit more clear, here is a continuum of elliptical polarizations. And so we'll go from a very skinny ellipse down the diagonal of the XY axis. It then passes through a circular polarization, then starts becoming an ellipse, and then eventually a linear polarization along the negative diagonal, and back and forth. And so from this, we can see that circular polarization and linear polarization are just special cases of elliptical polarization. So in some sense, everything is elliptical polarization. However, it's rare that I've ever seen a device designed to work for elliptical polarization. Usually we design things for linear or circular. Things aren't perfect, and we actually get elliptical. Combinations of linear and circular polarization. This is super important for a lot of reasons. We'll touch on a few here, but let's just talk about what happens when we bring two linear polarizations together. So we're not animating this right now, and this is a linear polarization that's linearly polarized along the x-axis. Suppose at the same time we have a second wave that is linearly polarized along the y-axis. And then let's sum these and look at them as if they were just a single wave. Well, we would get a linear polarization with slightly higher amplitude polarized along the diagonals. So that's still a linear polarization. We added two linears and got a linear polarization. Well, now what if we give one or both of these a phase shift so that these two linear polarizations were out of phase? This visualization is showing exactly that. I'm not showing the waves propagating, which is why I wasn't showing the propagating before. Instead, I'm just adding and subtracting phase to those two linear polarizations so that they go in and out of phase. And what we can see is that composite polarization. If we just looked at the sum and pretended it was just one wave, what we would be seeing, it goes through the full continuum of going through linear, through elliptical to circular, elliptical to linear, and all the way through these things. I think that's very interesting, but it illustrates that from two linear polarizations, we can convert that to any other kind of polarization just by delaying one relative to the other. So there's a device that we're not going to talk a whole lot about here called a wave plate that's intended to do exactly that. It will delay one of those linear polarizations relative to the other to do one of two things, either convert it to circular or change the handedness of the linear polarization. Here we're looking at the special case of when we add these two linear polarizations, we're giving the Y linear polarization 90 degrees of phase relative to the X polarization. When we do that, this gives us a left-hand circularly polarized wave. And we can see that. We pick a fixed point. We'll observe which way this is rotating. And from the perspective of the eyeball, this is definitely rotating counterclockwise, being left-hand circularly polarized wave. If we do the exact same thing now, but now subtract 90 degrees of phase instead of add to this Y linear polarization, now we get a right-hand circularly polarized wave. Now, something really cool happens when we add two circularly polarized waves. So one has to be left, one has to be right. And in this visualization, I'm not showing anything propagating. I am just adding and subtracting phase to the right circularly polarized wave. But what we can tell, regardless of the phase between the left and right circular waves, we always get a linearly polarized wave out. But that linear polarization has a tilt, and the tilt is controlled by the phase delay between the left and right circularly polarized waves. Well, there's a phenomenon called Faraday rotation. So there's devices that can literally rotate a linear polarization. And that seems super magical, but what's actually happening is the fundamental states in such a material are circularly polarized waves. So if you put a linear polarization in, that's just like you're exciting the two circularly polarized waves. The device inside, those two circularly polarized waves travel at a different speed. That's what leads to the rotation because that's changing the phase between the left and the right circularly polarized waves as they propagate. So it looks as if that linear polarization is rotating. But in fact, I think it's better to think of it as two circulars just traveling at different speeds and becoming out of phase. Then when it exits the device, it's a linear polarization in whatever that final tilt angle was. So two linears can give us circular. Two circulars always give us a linear. I think this causes enough confusion and uncertainty. It's worth stepping through the derivation to show that if we add two circularly polarized waves, a left and a right, with any phase between them, that we always get a linear polarization out, where the phase between them leads to a tilt angle. So we start by summing a left and a right circularly polarized wave, and you'll notice the only difference here is a plus J for the left circularly polarized and a minus J for the right. And then we also added phase to the right circular polarization. There is no phase term over here. So the theta represents the phase difference between the two. At this point, we can multiply everything out and then collect all of the common terms on the vector components. So we collect all the common things on the X component and the Y component, and we end up here. Staring at this, it's like we almost see the Euler identities here, but there's two complex exponentials either being added or subtracted. So to put it in that form, we can factor out an e to the j theta over 2. So we're only factoring a half of it out here, so we'll get an e to the j to theta over 2, but then we'll get an e to the minus j theta over 2 over here. So we go ahead and factor that out, and now we have things that look much more like our Euler identities. And in fact, that's the next step. We can write these two expressions as sines and cosines following the Euler identities. So just a quick reminder of what those are in the upper left. If we have the sum of two complex exponentials where they have opposite signs in the exponent, that's a cosine. And if we have a difference between the two, that's a sine. And of course, I didn't mention the factor of 2 or 2j there. Got to remember that. So this first one becomes a cosine, and the second one becomes a sine. Now, inspecting this, we can see that the x and y components are in phase. That's something we'll talk about later too, but that means we have a linear polarization. The two components don't have to be the same magnitude. If they are in phase, that's all we need to know. That's a linear polarization. And it has a tilt angle, in this case, theta over 2. So theta was the original phase difference between the left and the right circular polarization. The phase tilt is half of that. Poincare sphere. The Poincare sphere is a graphical technique for mapping all possible polarizations of an electromagnetic wave to some point on the surface. So let's just start with the equator. The equator maps all possible linear polarizations. So we could pick a point on the surface and call let's call that a 0 degree oriented linear polarization. If we come around the circle by 90 degrees, well, that polarization would have rotated by 45 degrees. We go to the opposite side of the circle, we would have rotated by 90 degrees. And if we keep coming around, well, we could call this 135 degrees or negative 45 degrees. Next, the circular polarization, so a perfectly right-handed circularly polarized wave is at the North Pole, and a left-handed circularly polarized wave is at the South Pole. That means the whole northern hemisphere are all right-handed circulating type polarizations. And then in the southern hemisphere, they're all left-handed circular type polarizations. I shouldn't call it circular because only the poles are circular. It's elliptical everywhere else. But right-handed in the northern hemisphere and left-handed circulation in the southern hemisphere. So really everywhere on this sphere, except exactly on the equator and exactly at the poles, are elliptical polarizations. So we could easily say that 99.9999999% of all polarizations are elliptical polarizations. Or I like to think of everything's elliptical, it's just special cases of the ellipse are either linear or circularly polarized waves. But I think one utility of this is that polarizations at opposite sides of the sphere are orthogonal to each other. So if they cross paths, they will not produce interference. And I think that's one of the biggest utilities of this. It's rare to see this used in practice. The only time I've ever seen it used in practice was the time I was using it. And I was working for a company. We had a fiber optic sensor that was rotating polarization. We were getting strange results out of this, and we just really couldn't explain it. And so I was pulled in to try to help explain that. And so what I did is I plotted the response of the sensor on the Poincare sphere. And what we saw is that the polarization was sort of walking circles around one quadrant of the sphere. So just looking at those raw results, that was really strange. But once we saw that, it became easy to interrogate that and figure out what the sensor was sensing. Otherwise, I've not actually seen this practically applied for analyzing things. It's more a graphical technique and a way to visualize polarization. To better illustrate that the Poincare sphere is really a continuum of all polarizations, I've came up with this visualization. So on the far left here, we're looking at the Poincare sphere, and there's a point that I'm picking on the surface, and this just wanders around randomly, although I sort of force it to go through the poles and linear polarization. But each one of those points corresponds to a polarization, and that's what we're looking at the lower right here, the the wave as it would correspond to the point we're picking on the surface. And we can definitely see as it approaches the North Pole, the wave starts looking much more like a right circularly polarized wave. And in the southern, a left circularly polarized wave, it passes through linear. But pretty much everywhere else is some sort of elliptical polarization. So I really like this type of visualization. I think it helps a lot to understand really what the Poincare sphere is representing. Again, it is just a map of the all possible polarizations. It's really not attempting to explain anything else. Polarization explicit form. Now we're going to dive into the math describing polarization. We had a few equations pop up earlier. I really didn't say much at the time. That's more meant for you once we go through this part to go back and see those equations in relation to the picture. But let's start off with realizing that the electric field E is perpendicular to the direction of K. Remember, polarization is all about the electric field, not the magnetic field. And that's simply because we would get the same answer with the magnetic field. But because the electric field is always perpendicular to the direction the wave is going, that means the polarization vector has to fall somewhere in the plane perpendicular to the direction of the wave. Now, this wave could be traveling in any possible direction. I know for simplicity, we've been letting this be the z direction, and that means these other two directions were x and y. But in general, we don't know that. In some general direction k, we have to decompose this plane perpendicular to k into two orthogonal directions. And we'll just call that a and b. So if k were in the z direction, well, a would be the x direction, b would be the y direction, but we can't say that because we can't guarantee k is in the z direction. So in general, this polarization vector is some kind of weighted sum of these two directions a and b, where this pa and pb are complex numbers, right? Because the component in each of the a and b directions can have an amplitude and a phase. Now, not all choices for A and B are possible. They have to follow some rules. The first thing is that A, K, and B all have to be perpendicular to each other. The second thing is it has to follow a handedness. And if we do a cross product, A cross B, that cross product has to be in the direction of K. So it can't be B cross A is in the direction of K. It would be in the direction of negative K. A cross B in the direction of K. And so go back to the x, y, z coordinates to help understand that. So if K were in the z direction, it would have to be x cross y to give us the z direction, right? Because y cross x would be the negative z direction. So as long as A and B follow those rules, then it's a valid choice for A and B. So we could also think of like A and B sort of rotating around just like P is, and all of those would be valid choices for A and B. Now later on, when we start talking about waves interacting with devices, the choice of A and B will actually become important. But just for a wave in outer space or in some kind of infinite medium, the choice of A and B does not matter as long as it follows these rules. The purpose of the math that I'm about to take you through is that we can write the expression for a wave in sort of I'm not going to call it a standard form because it's not necessarily a standard form, but it's a form that makes the polarization very explicit and very easy to determine. So we start off with just the polarization vector times this complex exponential, and I want to work with that to put it in a slightly more complicated form. But like I said, it's going to make determining polarization very easy. So the procedure would be you get an expression for a wave, you algebraically manipulate it to put it in this explicit form we'll get to, and then determining polarization is super easy. Well, we've already said this polarization vector has to be in a plane perpendicular to K, and we've chosen two orthogonal directions, A and B, to describe that. So this polarization vector is that weighted sum of A and B, where we have these two complex numbers, PA and PB, which describe an amplitude and a phase. So we can expand PA as a real valued amplitude and a phase. And similar with PB, a real valued amplitude and a phase. And they each have their own amplitudes and phase. Okay, well, let's take these expressions and plug them back into our expression for the wave, and we end up here. Now, this is almost in this explicit form, but we have a little bit of work to do to make this easier. We don't necessarily care about the phase of both of these. What we will care about is the common phase difference between them. So if we factor out this e to the j phi a from both of these terms and move it to the outside, then we'd end up here. Here's where we moved it to the outside. Since we factored out e to the j phi a, it's gone from this first term, but in the second term, we now have an e to the j phi b minus phi a. So this is the difference in phase between the A and B directions. And it'll turn out this overall phase, or the common phase between both of them, does not matter at all for polarization. It's just the phase difference and these two amplitude terms that we'll have to look at. So since it's just the phase difference, let's go ahead and just call that delta. And that's a much more common symbol for the phase difference between the two polarizations. The other thing we'll do is, rather than call this phi A, which we'll keep thinking, oh, that's the phase of the A direction, let's just think of this as the common phase, the phase that both of them share, and call that theta. Once we make those change of variables, now we arrive at the final expression, that this explicit form of polarization. And we have the polarization vector here. All the information about polarization is described by EA, EB, and this delta term. The theta does not matter, and this complex exponential out here with K and R in it also does not matter. So no matter what our expression is for the wave, if we can algebraically manipulate it into this form, we can extremely easily determine the polarization. So here we are. And remember, EA is the amplitude of the field in the A direction, and this is not a complex number. So it's just amplitude. And so EB, same thing, but not a complex number. It's a purely real number. We have delta, that's the phase difference between them, and then theta is the common phase, but it'll turn out theta does not matter. That's not controlling polarization at all. So to determine polarization, we're looking at EA, EB, and delta. So the first thing I look at is the phase difference between them, delta. If this is 0 degrees, or 180, 360, essentially integer multiples of 180 degrees, no matter what, it's a linear polarization. Does not matter what EA and EB are. If these two components in the A and B direction are in phase, we have a linear polarization. We're done determining polarization. Well, let's say they're out of phase. Well, the next thing I'll do is I'll look at that phase. If it is 90 degrees, or integer multiples of 180 after that, but let's just call it plus or minus 90 degrees, then I'm thinking to myself, okay, this might be a circular polarization, but I have one more thing to check for then. Okay, so they're 90 degrees out of phase, might be a circular polarization. Now I'm going to look at EA and EB. Are they equal to each other? If they are, that's when we have a circularly polarized wave, and then all we have to do is determine whether that is right-handed or left-handed. And so then we look at the sign of delta. If it's a 90 degrees, then it's a right-hand circular polarization. Positive 90 degrees, it's a left-hand circular polarization. If any of those tests are not met, then we have an elliptical polarization. And in practical terms, when you're really doing devices, we can't emit purely linear or purely circularly polarized waves. We can get really close, but they're never pure. So I would actually have to say, from a practical standpoint, everything will be elliptically polarized. One last warning, be careful about conventions. I want to talk about two conventions used in this video, but also throughout this course. The first is the sign convention. And this is how we express a wave traveling in the positive z direction. In this course, and what's common in most of engineering, is using what's called the negative sign convention. So something traveling in the positive z direction, we would write in frequency domain form as e to the minus jkz. And I guess the minus is what's telling us this is the negative sign convention. Now in a time domain form, we have a cosine of omega t minus kz, right? So we have time, and then we have this thing that's sort of a frequency for time. We have position z, and then this thing that's sort of a frequency for position. So k is like a spatial frequency, and omega is the temporal frequency. What matters is that these always have opposite sign for something traveling in the positive z direction. When we put the negative sign on the kz term, that's the negative sign convention. Well, we could assign a positive to the kz and a negative to omega t. That would be the positive sign convention. And I've seen lots of discussions online. One is fundamentally right, one is fundamentally wrong. They're both equally right and equally wrong. Well, neither of them are wrong. They're equally right. It's just a different convention. But you need to be careful about this, because when we're trying to label polarization, I'm saying things like a negative or a positive 90 degrees would lead to right or left. Well, if you switch sign conventions, things like that change, which is really why the way we define polarizations are meant to be independent of the sign convention. So whatever sign convention you're using, you have to sort of think through it and try to think what the rotations are doing. So the second convention in this course is I am using the IEEE definition of circular polarization, although I change it a little bit. So the IEEE actually defines it from the perspective of the receiver. But IEEE says a clockwise rotation is a left circularly polarized wave. I think that's very unintuitive. So I like to look at this in terms of the source, where you're looking down the same direction that the wave is propagating, and you're looking at the rotation at some fixed point. So a counterclockwise rotation is a left circularly polarized wave, and a clockwise rotation is a right circularly polarized wave. It's consistent with the IEEE definition. I just think a slightly more intuitive way to think of it and word it. But these are conventions, and you will find plenty of stuff out here that reverse that. This IEEE definition is definitely common in electrical engineering. This is an electrical engineering course, but I have 2 degrees in electrical engineering and 1 in optics. And when I was getting my optics degree, this sense of polarization was reversed. I didn't even catch on to the fact that there's all these conventions going on, and I was very, very confused until I sort of figured out what's going on. And so what an electrical engineer following the IEEE definition would call a left circularly polarized wave, I would have been calling a right circularly polarized wave while I was getting my degree in optics. So be very careful of that. And just because somebody says something in a paper, don't immediately assume you know what they're talking about. Try to dig into it a little bit more. And it's difficult because I think a lot of people just don't know that there's all these conflicting conventions out there.